Hello students, welcome to the class of Digital Signal Processing, and this is our fourth lecture on Fourier analysis. We were studying discrete time Fourier series. We did some numericals on that, and today we will be dealing with the properties of DTFS, and also we will be doing some numericals. With the properties, we will be dealing with certain numericals of this chapter, that is the discrete time Fourier series. So let's get started with it. We have already done these things. So we studied about the discrete time complex exponential also. Now it's our turn to study the properties of the discrete time Fourier series. So this one was the formula for the discrete time Fourier series. Now discrete time means the signal representation will be given by x of n. And the counterpart of that in the Fourier domain will be ck, or sometimes we denote it by xk. So that's it. And the formula that is given on the screen is this way: 1 by n. For ck, it is 1 by n. K is changing from 0 to n minus 1. And we have xn to the power minus j2 pi by n into kn. And this one is, there is no 1 by n over here. And this minus is changing to plus. And also for this case, what is happening is n is changing from n equals to 0 to n minus 1. So the first property that we have here is the linearity property, same as in the Z transform you saw that if there are two signals, so Z transform is given and we combine those two signals, then the Z transform of those two signals will also combine. The same thing is going to happen here. Still, let's see what is the property for the linearity property. So it says that if you have two signals, if the DFS of xn is ck, and discrete Fourier series for say yn is dk, then discrete Fourier series for axn plus byn will be becoming k into ck plus b into dk. Now let's go ahead and see one of the questions. The question is, the discrete Fourier series of x1n is x1k given as 1, 2, 3, 4, and for x2n it is 4, 3, 2, 1. What we have to find out is the discrete Fourier series of 2x1n plus x3 x2n. So see, the question over here is that you have two signals. The first signal is x1n. The second signal is x2n. So the discrete Fourier series for x1n is given as x1k. And the value for this is 1, 2, 3, 4. The discrete Fourier series for x2n is x2k. And the value for this is given as 4, 3, 2, 1. The question that they are asking you is, if you combine these two in this manner, that 2 times of x1n plus 3 times of x2n, then what will be the Fourier series coefficient for this xn? You have to find out the DTFS of xn. So as we have seen the property A into ck, so for x1 and the discrete Fourier series coefficient is given by x1k. So this is 2 into x1k plus 3 into x2k. This is it, what we have to do over here. Now, just multiply this 2 with 1, 2, 3, 4, and this 3 with 4, 3, 2, 1. what you will get is 2468. On this side, what you get is 12, 9, 6, and 3. So bitwise, you're going to add it 14, 13, 12, and 11. So this is the Fourier series coefficient of xn, which was 2x1n plus 3x2n. You can write this as xk is equal to this one. So this is the linearity property and a question on the numerical linearity property. And the next one is your time shifting property. First, let us see what is the time shifting property, and then we'll do the numerical on this one. So the time shifting property says that if the discrete Fourier series for xn is given as ck, then the discrete Fourier series for x of n minus n naught means the signal is shifted in the time domain, discrete time domain by n naught. In that case, in the frequency domain, the frequency coefficient gets multiplied with e to the power j 2 pi by capital N into n naught, small n naught, which was over here, so k into n naught. Now here you have to have this minus. So the way to remember is the minus over here will be remaining the same over here. Okay. Now e to the power minus j 2 pi k into small n naught by capital N. So this capital N is your fundamental period. Now let us see a question. So you have let xn be a periodic sequence with DTFS coefficients xk given as 1 j minus 1 minus j. So 1 is at x0, capital X0, j is at capital X1, minus 1 at capital X2, and at capital X3 it is minus j. So there is a signal, the example that is given over here is there is a signal xn, the DTFS or the discrete time Fourier series of this signal is given as xk, and the value for this xk is also given to us, and that is 1 j minus 1 minus j. The value is given as 1 j minus 1 and minus j. Now this signal xn is shifted by 1 unit. This is shifted by 1 unit, xn minus 1. And now we are required to find the DTFS for this one. So as we know, the DTFS is going to become xk into e to the power minus j k 2 pi by capital N into small n naught. In this case, my n naught is going to be equal to 1. So what we are going to do is xk, for every xk that we have over here, x0, first you will have x0, then you will have x1. So let us write here x0 into e to the power minus j into 0 into 2 pi by capital N into 1. The next one will be x1 into e to the power minus j into 1 into 2 pi by capital N into 1. Now, the second one will be, this is the counting weight is second. This is the third one, x2 e to the power minus j into 2 into 2 pi by capital N into 2. And the last one is going to be, the value of k is going to become 3. So it is x3 into e to the power minus j 3 into 2 pi by capital N, or 3 into 2 pi by capital N into how much? 1 again. Okay, so here there is a small mistake. This is going to be 1. So n naught is not changing for anyone. So it is 1 here also and 1 here also. This is multiplied by 1. This is multiplied. This is my k. The k is changing, right? The k is changing. So now if you see, the value is going to be for capital X0, the value was 1, and this whole thing is going to become 1 itself, so it is 1. For X1, the value was j, and this here, capital N is what? Capital N for our case is 4. The length is 4. The fundamental period is 4. Okay, and it should be given in the question. So capital N is given as 4. Now, x1 was j over here, x of 1, capital X of 1 was j. So we wrote over here j. Now, this is for k equals to small 1. This is 0, this is 0, this is 1, this is 2, this is 3. And what is this 0, 1, 2, 3? Which index is k? So this was for k equals to 0. Now this is for k equals to 1. See, now it is e to the power minus j 2 pi by 4. Capital N is 4. So that will become e to the power minus j pi by 2. Then the third one is x2. x2 is given how much? Minus 1. So first I will write here minus 1. Next thing is, this is the value of k is written here at this point. So e to the power minus j into 2 into 2 pi by 4. This is multiplication sign over here. Don't get confused. This multiplication sign. So 2 pi by 4 will cancel and become 2, and then this 2 and 2 will get cancelled. So how much is that? X2 is minus 1 into e to the power j pi, minus j pi. After that, we have the fourth one, that is minus j e to the power, how much? Minus j 2 e to the power minus 3j, right? And this is 4. So it will become 3 pi by 2 e to the power minus j 3 pi by. So this is your coefficient when what you are doing is you are shifting it in the time domain by 1 unit, then the Fourier series coefficient changes in this manner. Again, you can simplify this by breaking it into the Euler's cos and sine, but this is the final thing that you will be getting. The next property is the frequency shifting property. So here you see it was the time was shifted. In the time domain, it was shifted by 1 unit. Now we will see that if it is shifted in the time domain, we are having some frequency shifting. Then what is going to happen in the frequency domain? So if the frequency of the signal is shifted, the original signal extent, then what is going to happen? So over here it is called the frequency property. Let us see what I want to tell you. First, let us once again see the statement of the time domain. So if the discrete Fourier series of xn is ck and we are shifting in the time domain by n naught, and shifting in the time by n naught, not time domain. In the time domain, in time you are shifting by n naught, and in the frequency domain, the frequency is shifting by this measurement, e to the power minus j2 pi k n naught by capital N. Now what is going to happen is we are going to do the frequency shifting. So if the DFS of x of n is ck, and what we do is that we are finding the DFS of xn into e to the power j capital M 2 pi by capital N into n. So you are shifting by this n. Then here in the frequency domain, the frequency is going shifting by c k minus n. There is a shifting over here. So now let us see this question over here. So there is a periodic sequence xn with DTFS as 1, 2, 3, 4. So there is a periodic sequence xn. The DTFS or DFS for this is the discrete time Fourier series for this is xk, and this xk is given as 1, 2, 3, 4. N over here is 4. The indices are for 0. This is 1, this is 2, and this is 3. Now what we have been told is that we have to find out the DTFS for xn into e to the power. We have to find the DTFS for xn into e to the power j 2 pi small n by 4. So capital N over here is 4. Right, this is the question, j 2 pi 4 by n. So first of all, if we simplify this, it is going to become pi by 2 over here. Okay, first let us concentrate on what is going to happen with the Fourier series coefficient. As we know, it is going to become xk minus m. Now let us identify what is m. M in this case, let us see from here, 2 pi by n, when my n is equal to 4, n is written here, so n is already written, n is n, so capital M is equal to 1. In this case, capital M is becoming 1. So the Fourier series coefficients, they are going to change. So if your xk is now going to become what? X of k minus 1. So the first one, which was at 0, it will now become at x of minus 1. The one which was at x of 1 will become 1 minus 1, that is x of 0. After this, x of 2, the one which was at x of 2 will now change into x of 2 minus 1, that is x of 1. The third one, which was at x of 3, will now change into 3 minus 1, that is x of 4. And there was nothing at x of 4, so we don't need to write. So the final answer that we will be getting for this one, xk minus 1, will be at x0 we will have nothing, because at capital X minus 1 we had nothing, and the rest of the things are going to shift 1, 2, 3. This is the final one that we will be getting by using the frequency shifting property. So this is all about the frequency shifting property. If you had the signal xn, you had the Fourier coefficients given. Now you shifted the signal in the time domain, in the frequency domain, by e to the power j. You had done the frequency shifting of the signal, not the frequency domain. You are telling that in the time domain, you are multiplying the signal with e to the power j 2 pi n by 4. This means that you are doing the frequency shifting of the signal. Now, if you're doing the frequency shifting of the signal, then in the frequency domain, the frequencies are also going to change. So how is it changing? The frequencies will become x of k minus m. This was c of k minus n. Here we have taken that xn is xk, so it is becoming x of k minus n. Now let's move on to the next property, which is the conjugation property. The conjugation property is very straightforward. In the conjugation property itself, we will be telling you the time reversal property, because in conjugation both are happening. If DFS of xn is ck, then DFS of conjugate of xn, that is x star n, is actually what? C star minus k. So here only I am doing the time shifting property. If DFS of xn is ck, then DFS of, or DTFS, anything, these are the same thing, x of minus n will be c of minus k. So c of minus k you have to calculate here also, here also. So both are the same thing. We will be studying it once only. So for this question, you have been given that there is a signal xn. The DTFS for this signal, or DFS for this signal, is xk, and this xk is equal to 1 plus j, 2 minus j, and 3, 4. 1 plus j, 2 minus j, then you had 3, and then you had 4. So first, if we only had to take out x of minus n, the DTFS of x of minus n, the DTFS of this much, then it will be x of minus k. Means this is at 0, this is at 1, this is at 2, and this is at 3. So now what is going to happen is, it will get time reversed. So by time reversal, this is going to become 4, 3, 2 minus j, and 1 plus j. So 1 plus j remains on 0. This will come at minus 1. This will come at minus 2, and this will come at minus 2. So till here it is the time reversal property. So in case of conjugation, we use first time reversal and then we do the conjugation. Now if we have to take out x star n, then it is going to become x star of minus k. So if you see the first one, it is just the real part 4. The second one also you has only the real part. See, the third one has an imaginary part which will change from plus to minus or minus to plus. So here it was plus, minus, it changes into plus j. And this one was plus j, so it will be changed into minus. This is the answer for conjugation property. So for using the conjugation property, first you are doing time reversal and then you are conjugating. The part which is having the imaginary part, only that time you will be able to see the change. For those portions which are having only the real part, there won't be any change. Okay, now we have done this time reversal property together. Now the next property is the periodic convolution property. So the periodic convolution property, what does it say? That if you are doing the convolution in the time domain, it is equal to the multiplication in the frequency domain. That's it. So what does it say actually in the statement wise periodic convolution property? We are doing periodic convolution. So if the discrete time Fourier series of x of n, if DTFS of x of n is ck and DTFS of y of n is dk, then if you convolve this to signal DTFS of convolution of xn, convolution yn, the periodic convolution of these two, then this is going to be multiplied in the frequency domain, ck into dk. So how we write periodic convolution of this? Periodic convolution happens here. These two signals are periodic only. So k is going from 0 to n minus 1. This can be written as 0 to n minus 1. And say we are shifted it with, we are representing this by shifting after shifting as r. So n minus r. This is going to become ck into dk. Small change over here, n into ck into dk. Now let us see the question given over here. The question given is that x1n is equal to 1, 2, 3, 4. x1n is equal to 1, 2, 3, 4. And x2n is equal to 1, 1, 1, 1. What you need to find out is DTFS of the convolution of these two. You have to find out the DTFS of the convolution of x1n, convolution x2n. You have to find the DTFS of this. So this will be equal to ck multiplied with ck, but we don't have the ck and dk yet. So if I write the ck for this one, then how we can write it? Capital N over here for this case is capital N is equal to 4, right? So k, small k will go from 0 to 3 and small n will also go from 0 to 3. So what we are finding out is first we will be finding out ck. The ck, the formula for ck says that ck is equal to 1 by n. You see the formula over here for ck. 1 by n, k equals to 0 to n minus 1, xn e to the power minus j through pi by capital N into small kn. K equals to 0 to n minus 1, xn e to the power minus j through pi by capital N into kn. Now let's write this. We have to find from ck for C0. First one, if you find C0, it is 1 by 4. Now, just understand this, that k is 0. K is equal to 0. So, this is going to become 0. So, this full thing will become 1. So, basically, we have here is x0 plus x1 plus x2 plus x3. And in this case, what we had was x0, x1, x2, x3 was 1, 2, 3, 4. So 1 by 4 1 plus 2 plus 3 plus 4. That will give us how much? 10. Now the next one, if you see C1, if you take out, that is 1 by 4. In this case, it's not going to be k equals to 0 to n minus 1. This is going to be xn. Here, all my k's are 1, so I will directly write k1 and n is only going to change. So I'm just trying to make this expression simpler by simplifying these things. K equals to 0 to capital N minus 1. So now here it's going to become x xn e to the power minus j 2 pi by 4, that is pi by 2, right? Pi by 2 into, this time it is 1 into n. So this also gets cancelled. 2 pi by 4 was there, so 2 remains, okay. Now what we have, write it down here, 1 by 4. And just you see over here, it is first one will be x0, second one will be x1 into e to the power minus j pi by 2 plus x2 e to the power minus j pi by 2 into 2 plus x3 e to the power minus j 3 pi by 2. You'll find out the value. Same way you are going to find out x32 going to become large. So I won't do it, but I'll tell you the full method. This way you will find out C2, then you will find out C3. Then after this, you are going to find out D0, D1, D2, and D3. D0, D1, D2, and D3. Same method. After that, final answer will be C0, D0. Then you are going to multiply it, right? C0, D0, D1. So this one will be your final Fourier series coefficient for when you are convolving the signal, then it is the in the time domain. If you are convolving, then it is the multiplication in the frequency domain. So this is what you are going to do. Fine. Now let's go on to the next property, which is the convolution property, convolution and frequency property. That means in the time domain, you are multiplying in the time domain. So when you are multiplying in the time domain, what's going to happen? That in the frequency domain, you are going to do the convolution. So in this case, you can see the signals are given to us 1, 2, 1, 2, x1n, and 1, 1, 1, 1 is x2n. Now both the signals, if I'm multiplying in the time domain, x1n into x2n, and then they're asking me the Fourier series coefficient of x1n into x2n, then what I have to do is first I will have to convolve it. In the frequency domain, I'll have to convolve it. So what I need to convolve is the Fourier series coefficients for x1n and x2n. So first I need to find out the Fourier series Fourier series of x1n and x2n, and then only I will be able to convolve it, right? So that is the thing that you have to do. So in this case, you will first have to find out x1k, then you will have to find out x2k, and then you will do the convolution of that. And in the previous case also, what you had done was first you found out the coefficients, that is x1k and x2k, and then you are doing the multiplication. So in both the cases, you needed to find out firstly the Fourier series coefficient, because the Fourier series coefficient was already not given. In the previous examples, the coefficients were given, but in these two examples, although it is very long, but the Fourier series coefficient is not given. the signal itself is given. So first property says that the periodic convolution property, which says that if the two signals are convolved in the time domain, then in the frequency domain, their Fourier coefficients are going to get multiplied. But the Fourier coefficients were not given in the question. So we will individually find out the Fourier coefficient for x1n and Fourier coefficient for x2n, and then we will multiply for the periodic convolution property. And for the convolution in frequency property, that means you are having the multiplication of the two signals in the time domain. In that case, in the frequency domain, that those two signals are going to convolve. So here the signals were x1n and x2n. If you multiply these two signals, so what you can do is just simply multiply these two signals uh, in the time domain, and then find out the Fourier transform or Fourier series of that. That is also one way of doing it. First multiply it. If you multiply it, it will become 1, 2, 1, 2, because all over here is 1, 1, 1. So 1 into 1, 1, 2 into 1, 2, 1 into 1, 1, and then 2 into 1, 2. So 1, 2, 1, 2 will be xn. Then find out the DTFS of that. That will be making this property very clear. Now the final one is the Parseval's theorem. So the Parseval's theorem says that, now this is an important property again. So let us go through this. The Parseval's theorem. It says that for discrete time periodic signal, we have 1 by n summation, if you take over n equals to n mod of xn square, this will be equal to k equals to n mod of ck square. So in this case, in this question that it is given over here, you have to verify the Parseval's theorem by computing both sides. So xn is given to us. So xn is given to us as 1, 2, 1, 2. If you find out this side, xn square, that will be 1, 4, 1, 4. This capital N is 4. Now, if you do the summation from n equals to 0 to 3, it will be right. So it is from 0 to 3. If you add all these, then what will you are going to get is 1 plus 4 plus 1 plus 4 divided by 4. So this is 8, 9, 10 by 4. And on this side, what is going to happen? You have to do the ck square. Now the ck will, for that, you will need to find out all the ck. C0 will be 1 plus 2 plus 1 plus 2. But C1 again, you will have to find out. 1 plus 2 into e to the power minus j 2 pi by 4 into, this is k is 1 and n is also 1. Then it is 1 into e to the power minus j 2 pi by 4. K in this case is 1, but n is 2. And then you have again 2 into e to the power minus j 2 pi by 4 into n is in this case is 2 and k in this case is again 1. So what you get over here is 1 plus, this will be 2 into cos pi by 2 plus j minus j sin pi by 2. In this case, it is going to be again minus pi by 2. And that pi is also, that 2 is also going to get cancelled. So it is basically becoming cos pi minus j sin pi. Plus we have 2 into, again this part over here, k was 0, 1, 2. Here the k is 3. Sorry, not the k. The n is 3. So this is 3 over here. This is pi by 3. So this is going to become cos 3 pi by 2 plus j sin minus j sin 3 pi by 3. So this way you will first find out C1. Same way you are going to find out C2 and C3. After you get all these three values, C0, C1, C2, C3, then take individual square of this and add them. Means C0 ka square you will get 36. Same way take out C1 square, C2 square, C3 square and then divide it by 4. Divide it and then check whether these two parts are equal. 1 by n xk square and xn square. Both if they are equal, then the Parseval's theorem, the property is getting satisfied. And what is the Parseval's theorem? It says that the energy of the signal in the time domain and the frequency domain remains the same. So with this, we have covered all the properties of the discrete time Fourier series with the small questions. You can pause the video and do these questions and get the complete answer. I will be posting the complete answers in the comment section. So you can just do it, try it and put the answers there. Thank you everyone. Let's meet in the next class for DTFS.